Hello and welcome back to the second part of my presentation on chemical kinetics. Today I'll be talking about this quantity known as the activation energy, which I've introduced in the first part of my presentation, and its physical significance for elementary reactions and for multi-step reactions. Our discussion will center on two key questions. Can the activation energy for a reaction be zero? And can it ever be negative? I'll be spending most of my time discussing the second question, as the first question can be easily answered. We will first need to gain a better understanding of why reactions have activation energy. So as you can see in this energy profile diagram, right, energy profile diagram, as the reaction starts, the potential energy of the system begins to rise, right? And once it is past this energy maximum, right, this peak here, the potential energy will then begin to decrease until it reaches the products. Physically, what this would mean is that at the start, in the first half, more energy is used up or consumed than it is released. While in the second half of the reaction, more energy is released than it is used up. And so now our question becomes, with this understanding, our question naturally becomes, what is consuming so much energy at the start in the first half of the reaction, such that the consumption of energy is greater than the release of it? Now there are several factors responsible for high energy consumption, right, at the start of the reaction, but I'll just name the key few. I will illustrate these factors using the SN2 reaction shown here. At the start, right, some bonds need to be broken. In particular, for this SN2 reaction, the CCl bond needs to be broken, and that requires energy. Not only that, we also see a geometric change in the configuration of the molecule. So here it is a tetrahedral geometry, and towards the transition state, when it becomes the transition state, it adopts a trigonal bipyramidal geometry, which is also much more strained compared to the tetrahedral geometry. So this transition state is hence also higher in the energy in a sense because it is more strained, right? Also following the changes in geometry, there's also a change in the hybridization states of the carbon atom in this molecule. So here in the tetrahedral geometry, it is sp3, and going to the trigonal bipyramidal geometry of the transition state, the carbon adopts sp2 hybridization. Right? So because of this rehybridization, energy is also consumed. And not to forget, when the nucleophile approaches the electrophile, there may also be some repulsion between their electron clouds, and that would also require energy to overcome. So you may ask, why then may the energy fall after the peak is reached, after the energy maximum is reached? Well, there is a lot of bond forming, right, occurring, right, that releases energy, not just between the atoms, right, but also between the molecules and ions and the solvent molecules surrounding them in the reaction medium. At the same time, more importantly, we are also going from this very strained trigonal bipyramidal geometry back to a tetrahedral one, which is less strained. So this release of strain is also energetically favorable. Not to forget, there is also a dispersal or sort of a negative charge, right? So here you see hydroxide bearing the negative charge. In particular, the oxygen is bearing the bulk of the negative charge, and oxygen is smaller compared to chlorine, right? So with chlorine, there's a bigger atomic volume. The negative charge is dispersed over a larger atomic volume, and hence going towards the products, there's also energetic stabilization from greater dispersal of negative charge. Now that we understand, right, the small energy changes that take place during a reaction and how activation energy arises, it is not too difficult for us to see why some reactions don't have an activation energy. If a reaction was to strictly give off more energy than it uses at all times during the progress of the reaction, then wouldn't the potential energy keep on decreasing until it reaches the products? and such reactions do exist. Consider the combination of radicals to form a molecule. Perhaps there may still be some electronic repulsion between them during their approach. Let's say, for example, the chlorine atoms approaching each other. There may be some electronic repulsion, right? And hence using up some energy, right? But because there is no bond breaking, and bond breaking is the one that really is really endothermic, using up a lot of energy, right? Because there's no bond breaking, right? The energy used up is much less than the energy that is released due to the bond formation, the CCl bond, the ClCl bond formed, right? That is formed during the reaction, right? This releases much more energy than that is being used to overcome, let's say, the electronic repulsion between the initial electronic repulsion between the chlorine atoms as they approach each other. These reactions are said to be barrierless, as they do not have an activation energy barrier. So other examples include the combination of hydrogen atoms to form dihydrogen molecule, as well as the combination of methyl radicals to form ethane. If you want to take a look at the potential energy changes during such a reaction, such a barrierless reaction, I have a diagram for you here. And I think this is one which you should have seen in the topic of chemical bonding, right? It shows the potential energy varying as a function of the distance, the internuclear distance between the two atoms, as they approach each other from a very large separation, right? In the direction, right, of the arrow pointing here, in this direction, towards the equilibrium bond length, right? Bonding interactions cause a lowering of the potential energy, and at the equilibrium bond length, the potential energy reaches a minimum, right? And so you see that there's no hump. Usually there will be a hump, right, to indicate the presence of a non-zero activation energy. But in this case, the activation energy is 0, and this goes the potential energy just flows smoothly downwards towards the products. Now we will go on. So now we have answered the first question on whether reactions can have zero activation energy, and indeed they can have. What about negative activation energy? Since activation energy has been defined, right, as the minimum energy that the reactants must possess for the reaction to occur, it certainly must be at least equals to 0. Because, if you think about it, a reaction either requires an energy input, that means to say the activation energy is more than 0, or it doesn't require an input, that means to say that the reaction has 0 activation energy, right? So it either requires an input or doesn't require an input of energy, right? So in that sense, reactions can't really have, elementary reactions, right, can't really have negative activation energy. We can also consider this from a mathematical point of view by looking at the Arrhenius equation, right, which relates the rate constant to the temperature and the activation energy. So if the activation energy were negative, right, if it was negative, right, then what happens? So then if you consider the exponent negative EA to the over RT, right, the exponent would be positive. The exponent will be strictly positive because negative, and if negative EA, right, so negative EA is positive because EA is negative, right, and then negative EA over RT, so RT, they're all positive quantities, and so negative EA over RT would be a strictly positive quantity if EA was to be negative, right? And so by increasing T, by increasing the denominator in the exponent, right, and when this whole thing is actually, this exponent is actually strictly positive, by increasing the denominator's size, we will expect the exponent, right, to become smaller and smaller, right, to decrease essentially. And if the exponent were to decrease as T increases, the exponential, right, factor e to the power of negative EA over RT would also decrease as temperature increases. And hence, if EA was negative, increasing temperature would lead to decreasing rate constant. And would that make sense for a single elementary reaction, for a single elementary step? I think it wouldn't make sense, right? Because by increasing the temperature necessarily leads to, increasing T necessarily leads to more A and B, So let's say you consider the elementary step A plus B colliding with each other to give AB, right? Increasing T will necessarily lead to more A and B having sufficient energy for effective collisions between them. If you look at you still remember our Maxwell-Boltzmann distribution from the previous video, you would think that more particles would have sufficient energy when T increases. So it wouldn't make sense, to have the rate decreasing as temperature increases, right? So from viewing the matter from these two perspectives, from an intuitive perspective, based on a reaction should either require an energy input or doesn't require energy input, and from this mathematical perspective, right? From these two perspectives, I think we should be convinced that negative activation energy would not be possible for an elementary reaction occurring in a single step. So an elementary reaction is basically a reaction that cannot be broken into simpler steps, right? Cannot be broken into simpler, so it just occurs in one straightforward step, no other steps, or including reverse steps and no reverse steps, right? Okay, so let's move on. So if any single elementary reaction cannot have, right? So as we established, any single elementary reaction cannot have a negative activation energy, then would you not agree with me that for a reaction that consists of a sequence, right, of a sequential set of forward elementary steps, for example, as I've written here, A plus B to give AB, AB plus C to give ABC, ABC plus A to give D, and D being the product that you obtain from reacting A, B, and C. So all these steps all move forward, right? For this reaction scheme, A plus B plus C to give D, right? So all these steps are all forward steps. There are no reverse steps. So if every single step here has a positive activation energy, then it would follow that the overall reaction would also have a positive activation energy. It means that as temperature increases, the rate constant for this reaction will also increase, right? It makes sense. Okay, so in general, we can establish that for all reactions that consist of only forward steps and negligible backward reactions, the activation energy cannot be negative. But what about so as you can see, I think you are beginning to see when can reactions have negative activation energy, and it is when they have very significant backward reactions, right? And that's the condition, right? So let's say you look at this particular this I can highlight this. So you look at this side, right? This reaction scheme, A plus B to give AB, AB then dissociates to give back A plus B, right? And then AB reacts with C to give D. So you can see that, okay, so this is basically the same sort of a reaction. It's basically A plus B plus C to give D, right? You can see the overall reaction is the same as this one. This one is A plus B plus C to give D. This is also A plus B plus C to give D, but it reacts in actually no. This is, sorry, my apologies. This is actually not the same. This is 2A plus B plus C to give D. This is just A plus B plus C to give D, but it doesn't matter. They need not be the same, right? But my point is that you see here the highlighted in bold, there is a reverse step. So there's a dissociation of A, B to give A and B. The complex AB to give back A and B. So because of this, there's a backward step, and so the activation energy is no longer so trivial, and because of this backward step, it is I will show you later that actually it is possible, right, for reactions, multi-step reactions with backward steps that are significant, to have a negative activation energy. It may sound a bit confusing now, but I will demonstrate for you later with an example. In fact, it's the next slide. Yes. So let us consider the following reaction: the oxidation of nitric oxide NO by oxygen to produce NO2. I will now tell you straight up that it has a negative activation energy, and I will show you how that can be possible. This reaction proceeds by a two-step mechanism, right? However, for the first step, which is the association, I call this association of the two NO molecules, right, to form a dimer. The dimer is N2O2. there is also a significant backward reaction, which is the dissociation of the dimer to form back the NO, the two NO molecules. So essentially, the second step right here is not a second step, but there is this particular backward step that is the reverse of the first step, right? So essentially, this is similar to our, our example scheme here. A plus B to give AB. AB dissociates to give A plus B is similar to this, right? Yeah, so and each of these have their individual rate constants. So the first step, the first forward step is rate constant K1. The second, the reverse of the first step, it has a rate constant K negative 1, subscript negative 1. And for the last one, it has K subscript 2, right? So the first step, the reverse of the first step, and the second step. Yeah, okay. Since all three steps, the whether it's the forward step, the reverse steps, right? The forward steps or the reverse step, right? Are elementary reactions. They are all elementary reactions. All of them must have an activation energy individually that is at least equals to 0. So I'll not say that it is positive, because the first step being an association step means there's just bond forming. Maybe that the activation, I mean the the activation energy may be close to 0, right? Because as we mentioned before, if there's just bond forming, the reaction may be barrierless. So I would say that maybe the activation energy for the first step may be very close to 0, or yeah. So that's not really that important. It's just a technical detail that will not spend too much time talking about. So yeah, so I think we can all agree that all the three rate constants, K1, K negative 1, and K2, would all increase, right, when temperature increases, because all of them have a activation energy that is positive, right, sort of positive, right? So based on our Arrhenius equation, K equals to A e to the power of negative EA over RT, right? Because based on that relationship, as temperature increases with a positive activation energy, right, rate constant should increase, okay? Now, the key to why this reaction has a negative activation energy overall, not for the individual steps. The individual steps have at least equal to 0 activation energy, but I will tell you overall, right? Overall, the combination of these three steps, the reaction has a negative activation energy, and I'll show you in the next slide. Now, let's say we increase temperature. Now we need to ask ourselves, would all three rate constants K1, K negative 1, and K2 all increase by the same extent? Now it turns out that K negative 1 actually increases to a much larger extent than K1 and K2. And this is the cause of the negative temperature dependence, right? This is because when temperature increases, okay, let's look back at the second step. This is because when temperature increases, the dissociation of the dimer N2O2 becomes much more favorable, and it makes sense because dissociation of dimer is an endothermic reaction, right? So when we increase the temperature, the position of equilibrium will lie further to the right? So it makes sense that it's more energetically favorable, right, as temperature increases for this dissociation of dimer to occur, and hence it does increase in rate much faster, right, than the other two reactions. Right, the two other forward reactions, right, and yeah, so and because of this, right, the backward rate increases much more. So when we increase the temperature, the backward rate of reaction increases much more. At least for the second step, when I talk about the backward rate, I'm talking about the second step. The backward rate increases much faster than the forward rates of the forward steps as temperature increases, and so the overall rate slows. The overall rate of reaction, the overall oxidation of NO to form NO2 slows down as temperature increases. And this is what negative activation energy essentially means. It means, right, it essentially indicates a negative temperature dependence, right? That means to say that when temperature increases, the activation energy the temperature increases, the rate of reaction, the rate constant would actually decrease, right? And mathematically, based on the Arrhenius equation, it does make sense. So if you see here, negative as I explained just now, actually I've explained this previously in this slide, right? When we talk about the mathematical relationship, just that exponent, if EA was negative, the exponent becoming smaller, right, as the temperature increases, because T is the denominator of the exponent. So as it increases, the exponent becomes smaller, the exponential factor e to the power of negative EA over RT becomes smaller as T increases when EA is negative, and hence increasing temperature decreases the rate constant. I can also prove, if you can't see that, don't worry, if you want more concreteness, I have written a proof, mathematical proof here, in this handwritten proof, right? So if you just consider, right, K equals to A e to the power negative EA over RT, and just assume the pre-exponential factor A is independent of temperature, where I can just do a simple differentiation, right? And you can just, it's just differentiating in an exponential form, and then you get, in the end, you just get A times EA over RT square times the exponential factor, right? And so you can see clearly, right, the exponential factor is at least is more than 0, right? So the exponential factor is more than 0, A is more than 0, RT square is also more than 0. So the only thing that determines the sign of dkt by dt is just the activation energy, right? So activation energy less than 0, dk dt, right? The rate of change of the rate constant with respect to temperature becomes negative. And when EA is more than 0, the rate of change of the rate constant with respect to temperature becomes positive, right? So as EA is less than 0, when EA is negative, the rate constant decreases with temperature increasing, while for a positive activation energy, which is most usually the case, the rate constant increases as temperature increases. So this is a simple proof based on some simple calculus. So if you don't appreciate this, I mean, if you don't understand this or you haven't learned calculus before, it doesn't matter, because I think just thinking about it in a mathematical way previously is sufficient. This is not necessary, but for concreteness, I will show this. Yeah. So the next slide. Yes. So if you perform a particular mathematical treatment called the steady state approximation, which is also discussed in the elements of physical chemistry, right, by Paul Atkins and Giulio Di Paula, right, Peter Atkins and Giulio Di Paula, right, this book, it also discusses, right, this steady state approximation, but I will not go through it, right, because it's a bit math heavy, so I will just say by the steady state approximation, it is possible, right, to find that the overall rate constant, so for the overall reaction there is an overall rate constant, right, and which can be expressed in terms of the individual rate constants for the individual forward and backward steps, and it turns out that it can be expressed as K1 K2 over K negative 1. So if the reverse rate constant increases much more with temperature, right, means the denominator increases much more with temperature, we see that the overall rate constant would decrease as temperature increases. And for those of you who are also more interested in this and the mathematical manipulation, you can try to derive that the overall activation energy for the reaction is actually EA1 plus EA2 minus the activation energy for the reverse step. Okay, this can be obtained by doing some mathematical manipulation, right, and making use of the Arrhenius, the rate constant form in the expression of the Arrhenius equation. But I will not delve on that too much, because this is just for those who are more mathematically able and really want to try it out. You can go and try it out, but it's not really necessary to understand this. Okay. Now we're going to go to the last parts of this presentation already, right? So I'm going to ask this question: how do we calculate the activation energy for a multi-step reaction? Or is it possible for us to tell what is the activation energy for a multi-step reaction? So I've prepared this diagram crudely drawn on paint, but I think it will help understand this help you to understand this a bit better. So let's look at this diagram, right? Energy profile diagram. Can we say that, okay, so I think the rate determining step is pretty obvious, right? It's the one with the largest activation energy, right? So it will be this, the first one from the right, this tall green arrow, right? The tallest green arrow, actually. It will just be this. The rate determining step will just be this step. But can we say right, that the activation energy for the reaction, this entire reaction, is just this tall green arrow? Now the answer is no, it cannot. And that, for the activation energy for the entire overall reaction needs to be expressed in terms of the activation energies of not just the forward steps but also that of the reverse steps, as we can see, in this expression. For even just this simple two-step mechanism, right, of oxidation of nitric oxide, the activation energy needs to be expressed not just in terms of the activation energies of the forward steps but also of the reverse step, which is in this case very significant, right? So similarly, for this multi-step reaction, there is also a need for us to, essentially for a multi-step reaction, you cannot just take it to be the tallest, the greatest, the activation energy of the rate determining step. It's not just so simple. You need to do some mathematical treatments, find the rate constant form in terms of the individual rate constants of the individual steps, and then from there obtain what is the activation energy. Not so simple as just reading off the graph, the reaction energy profile diagram. Not so simple. So, right now with this, I want to summarize what we have gone through today with the last slide. So the answer for this is that it can be, the calculation can be done, but it's not so simple. We need to do some mathematical treatments first, okay, for a multi-step reaction. All right, this is the summary slide. So we have all these different interpretations of the activation energy. So how really to the beginner chemistry student, how should we view, to not have the incorrect view, to have the correct view of the activation energy, and yet a simple view. Let's strive for a simple view, simple and chemically correct view. So how should we view it? So I would think that for an elementary reaction means that it proceeds by just one single step, like a single collision between two particles, for example. We can see that it is just a big hump in the activation energy and the reaction energy profile diagram, like for example this one, right? If it's just a simple one-step process, like maybe SN2 reaction, it's just this big hump for an elementary reaction. Yeah, but for a multi-step reaction, like what I've drawn in this diagram, sorry, not this one, it really cannot be viewed as a big hump, because for this one there are multiple humps firstly, right? So it's not just the size of the biggest hump, it's more than that. It needs more rigorous mathematical treatment. So we can no longer take this view that it's just a big hump on a diagram. We should instead see, okay, the activation energy, the overall activation energy of the reaction, of this multi-step reaction, which can be calculated by mathematical treatments, right, as an indication of how the rate changes with temperature, right? If the rate constant were to decrease as temperature increases, we will say that the activation energy, the overall activation energy of the reaction is negative. If the rate increases as temperature increases, then the activation energy of the reaction would thus be positive. So this does make a lot of intuitive sense. We should just view it, right, as essentially the activation energy essentially tells us the temperature dependence of the rate constant, and that is how we should see it for a multi-step complex reaction. For an elementary reaction, yes, it is the minimum energy required to kickstart the reaction, but for a multi-step one, not so simple view that we can take. Instead, you should take it as the how does the rate constant vary with temperature. That is it. So I think I will end this presentation now. I hope I didn't confuse you, because for this video I did much more mathy stuff, a lot more maths involved, right, especially with the calculus part as well. But I hope that it didn't bog you down. I hope you were still able to discern, right, distill the essence, right, the essence of what I'm trying to tell you, the concepts, and sieve away the maths. I try to take away the maths for most of it. For example, I didn't go through the steady state approximation, because this is just it's more of a means to an end, right? I'm trying to get I'm trying to tell you that I got this expression via my mathematical treatment. Otherwise, you'll be asking me, how did I get the rate constant expression here, right? So I'm just telling you I got it from a mathematical treatment, and it looks like this. So yeah, to those of you who are interested in kinetics, maybe you can go and explore these concepts and treatments like the steady state approximation and other things, of course, in the textbook that I recommend by Peter Atkins and Paula Di Giulio, and this one. Yeah. And if you do have any questions, if anything is puzzling you at this moment in time, and if you felt that I didn't clarify any concepts, right, in this entire presentation, right, from even also from the part one as well. The part one, if you feel that, if you watch the video and you feel that anything is not clarified properly, then perhaps you can seek additional clarification in the comment section. Yep. So with that, I have nothing else for you, and I hope you did appreciate, right, my presentation and did gain a deeper understanding of kinetics from my presentation. So I'll end it here. Thank you very much.